Hey math people, definite integrals involving a U-substitution. Okay, you may have felt okay after a U-sub, maybe. I don't know, I'm thinking back to the Calc 1 days, back in my glory. And U-sub ain't too crazy, but the moment you throw bounds in, it does add a little bit of confusion to the mix. Oh, do I switch bounds? Do I go back to x? What do I do? Okay, I will guide you in that process. U-sub. This is nice when the integrand doesn't look immediately integratable. Sure, yeah, okay, in this problem that we're looking at right here, negative 8x times the quantity of 2x squared minus 2 all cubed, sure, you can do algebra here. You can write this 2x squared minus 2, you can write it out, I don't advise this, 3 times over. 2x squared minus 2. And then you got this negative 8x here. And yeah, you can FOIL or distribute this out. Feel free. It's going to take you a long time, so I wouldn't advise you to do that. There's a more clever approach to a problem like this, and that's to perform a U-substitution, which allows you to manipulate the variable at play, making the expression a little bit more in your favor. So this is how I teach U-sub. First off, pick a U. What would make sense? What would make sense? If I want to get rid of an expression, aka here this negative 8x, I need to be clever in my choice of u to make the derivative of u something that's going to easily cancel out, go away in the process. Here I'm going to say, well, u, if I made it negative 8x, that would not help me at all, because my du dx, my derivative, would just be a constant negative 8, and that wouldn't help me in the slightest in this problem. The problem here is actually this x. This is going to cause a little bit of an issue. My suggestion is whenever you have a big thing and there's some sort of function being applied to it, maybe it's a sine, maybe it's a natural log, maybe it's a cube, that's usually your best bet for your u. And in this case, it's going to be 2x squared minus 2. Okay, so how is that going to help me get rid of this x here, or this negative 8x? You'll see. Let's keep going here. I want to take the derivative, which is going to be du dx. So the derivative of this expression, take this 4 up front, it's going to be 4x, and the derivative of a constant, it's 0, it goes away. So I know that, and I'm going to treat this kind of like a fraction here, which is illegal in some ways, but for the sake of the problem, it's totally okay. I know that my du is equal to 4x dx, and that's going to help me in my substitution right here. Alright, so this is the inevitable conversation. The U-sub, so maybe, hopefully, you're watching this video knowing what a U-sub is, but the moment it's definite, it feels like you're juggling too many things at the same time. The bounds do change. So this is going to be my substitution for the integrand, what's going to be inside here. Great, but there's a little bit more to it when you have definite bounds. What you need to do is you need to recalculate the bounds on top of this. It's one of the two options, and I'll show you. Maybe with number 2, I'll do it a different way. So with number 1, I'm going to change the bounds, all right? And so that way I'm going to stay in u world. I'm going to stay with variable u for the rest of the problem thereafter. Here's the thing. My upper bound was in the x world 1. However, there's a relationship between x and u, and it's right here. I actually need to take this upper bound, and I need to plug it into this expression to get a new one. So in this case, my upper bound will be 2. Plugging in this 1 for x times 1 squared minus 2. My new upper bound for this expression is going to be 0, because 1 squared is 1, 2 minus 2 is 0. Let's do lower bound. So for the lower bound case, I'm plugging in 0 to this expression, so it'd be 2 times 0 squared minus 2. Okay, this is just 0. 0 minus 2 is negative 2. All right, so since I am now about to convert from the x world to the u world through this substitution, I am now switching the bounds along along with it. So, yeah, we can say that this is actually equal to. This is equal to. Now evaluated from no longer 0 to 1, but now from -2 to 0. Let's keep this here for now. You'll see that something magical is going to happen with it because of what my du is equal to. So I have this annoying -8x here. And we're going to cross our fingers and hope that it cancels out, and it will, because we chose the right u when we do some substitution here. Now, I know that this 2x squared minus 2 is u. So, yeah, we're going to do that. We're going to say, well, my u is 2x squared minus 2. I'm going to sub that right on in. Okay, next part is my dx. So I didn't quite finish this problem right here. I should have performed one last step here. I'm solving for this dx. So just divide out that 4x onto the other side. I can say dx is equal to du over 4x. Whoops, there we go. Alright, so I have this dx here, and I have what dx is equal to. So I'm going to plug that in. I'm going to say du over 4x. Let's look to see if some algebra is going to help us, and the idea is that it does. Sure enough, yeah, it does. These x's cancel right here. And you have -8 over 4. That's -2, and you can bring that up front. So we'll have -2 from -2 to 0. And what does this clean up to? Because I just brought this constant up front and those x's canceled. Actually, this is just good old x cubed du. That's pretty nice. That is an easy thing to integrate. Since I switched the bounds, all I need to do is just evaluate this. I did all the hard stuff. Now is the easy part. This is going to be -2 times 1/4 u to the 4th from -2 to 0. We like the 0 because if you plug in 0 that goes away. And then we can plug it in now. We'll show all of our work here. It'll be -2 times 0 minus 1/4 times -2 to the 4th. And will be our final answer. -2 to the 4th is 16. So this is going to be a -16 over 4, which is a 4. And then 4 times -2 is -8, our guy. -8, our guy. Winner is +8. Uh-oh. Yeah, +8 makes sense, because this is a normal 16, because it's to the 4th power, but then it's negative. So it's a -4 times a -2. So that makes sense. Good. 8 is our answer there. Switching the bounds, which is what I did in red, allowed me to not have to worry about switching back to x after I plugged in the u. The moment I switch to u and I switch the bounds, I stay in this u world with u in play for the rest of the problem until the answer. There is another way though. If you don't like this, oh man, I gotta switch the bounds, how do I remember how to switch the bounds approach? I have another answer for you, and let's do that approach for this problem. So I will not be doing this step in red here, and you'll see the alternative method to that right now. Alright, so begin to think about your choice of u. Very similar to number 1 in that aspect. So these are polynomial expressions. This is rational, but you get the idea. It's a ratio of polynomials. Doesn't have any like trig or sine or cosine or natural log business to it. So usually it's the thing in parentheses. That's just a heads up on that. If it's a polynomial or a rational, it's usually the thing in parentheses. Not always, but in both these cases, it is. So, yeah, let's make our u the thing in parentheses here, which is this expression. To the second, it's just going to be the 3x squared plus 2. So that's going to be my u. I'm going to say u is equal to 3x squared plus 2. Let's be a little bit smarter this time around. Last time I didn't solve for dx, I just solved for du. Let's actually solve for dx as well. So I'm going to say du dx is equal to 6x. And can we big brain this? Can we skip that middle step? I would multiply by 6x, and then I would divide by 6x. So dx should equal to du over 6x. That should help. All right, I'm not going to worry about the bounds. And in this approach, what I'm going to do is I'm going to view it indefinitely. I'm going to use this as a vessel to find the indefinite integral, and then I'm going to go back to the definite case. Something minor if you're going to do it this way, you can't have a nice string of equalities. Here, you can't. You can have a nice string of equalities. This is that, then this, then sure, then yeah. And final answer. You can't do that here because you're going to evaluate an indefinite integral and then like reapply it back to the expression with the old bounds, going back to x world. So just a heads up on that. It can't be a pretty string of equalities. Okay, so let's view this way. I did not say equal sign here. I'm saying, okay, now just consider the integral. Let's perform the u sub now. Okay, so 12x is still up top. Down below, I do have my u squared. And then my dx is du over 6x. Okay, well, some nice things happen here. Cancel, cancel, and then 12 over 6 is just 2. So this expression is equal to 2 times the integral of u to the negative 2 du. Okay, what is this antiderivative? So I should kind of do the same thing I did over here. I added 1 to the power, so I'm going to add 1 to this power to get negative 1. Okay. And then I should make it a negative, right? Because if I did normal derivative power rule stuff, bring this negative 1 up front. Yeah, so this is the correct antiderivative. Sure, I would need the plus c here. And I guess since it's indefinite, okay, just for the sake of being as mathematically correct as possible, I just borrowed this really quickly. So what I could do is this expression right here, which is negative 2 over u. Actually, I should have done that because that looks prettier, right? This is equal to negative 2 over u. There we go. And then sure, plus c, right? I want to borrow this. I'm going to say that this now, and now I'm going to go back to the equal sign, just like how I used it over there. I'm going to say that this expression is now equal to negative 2 over, I'm going to go back to x world now. Instead of writing u, I know what u is. I defined it earlier. It was 3x squared plus 2. So I'm back in x world. So I'm back to using the old bounds from negative 1 to 0. So this allowed me to avoid this upper-lower bound idea. Sure, I had to still do a decent amount of work for it, but I don't know. It's something that you have to pick your own poison with. I actually do prefer switching the bounds. I think that not having to worry about like this process, and after you just switch the bounds, I think that's a little bit easier in my mind, but who knows, maybe you prefer this, because now I'm just evaluating on the bounds. If I plug in 0, this goes away, so it'd be negative 1, and then minus, I gotta write this one out entirely, sorry. Negative 1, okay, so this is gonna be 3, negative 2 over 3 plus 2, which is 5. So that's negative 1 plus 2/5. Is that negative 3/5? I'm going to say it's negative 3/5. Yeah, negative 3/5. Okay. Pick your poison, man, right? Whatever you want to latch onto, whatever method you think is best, your call. So to summarize, when you have a definite integral and you're going to use a u-sub, you have to make a choice. You either need to switch the bounds and stay in u world and evaluate with u in mind, with those new bounds, or go off to the side, do an indefinite integral with u, and then get the answer, get the antiderivative, and then go back to x world and evaluate on the old bounds. Make your choice. I'm going to ask you to continue the math on, and I will do the same. I'll see you in the next video.